Bonjour à toutes et à tous.
Hello everyone, I'm going to present our activity on the deformation of structures, which was done by Mr. Maudi and Mrs. Sonal. So the objective of this work was to analyze the measures of deflection basins and to look at the sensitivity of these measurements in terms of the finite elements. We looked at the delamination and vertical cracking without propagation, whether this was vertical or transversal in 3D geometry. And then afterwards we looked at the propagation of 3D geometry in infrastructures, propagation of 3D cracks at the boundary elements. The main degradations that we looked at for the finite elements were the delaminations between the layers. We looked at surfaces of large 75 square meters in a comparison with Alizé. We looked at this surface or the lamination that were reduced with just a few square meters between asphalt layers. And so we looked at the transversal cracks or longitudinal with spacing of about 1.2 meters, and then we looked at the thickness. The deflection were calculated in absolute terms, and we simulated measures like the various diameters. The structures that we looked at a thick asphalt and two flexible road structures, and the properties come from Philippe Gabory's thesis, characteristics of linear characteristics. The change that we consider was a curvometer. So we looked at half the load on a surface of 5 by 15 meters, and we can see here how you can see the front and back pneumatic effects. We look at the short cracks of 1 meter or even sometimes 2 meters for the back axle, and then this allowed us to look at the delamination between different layers at different depths. And when we look at the finished elements and the different intensities of loads in this grid. The first stage meant that we compared the analytic that we did with Alizé and the calculation of finished the finite elements with César. So we looked at one delamination surface where we took the surface area off completely. So this gives it 75 square meters, and whatever the altitude of this delamination, we have analogous between Alizé and César with a slight loss of quality with the depth, and these were reduced in thickness when the depth increased. The property of the elements, the finished elements that were chosen for the interface, had a perfect slide and the opening of the crack with an interface with the RT value, and the elasticity module was represented here. So we simulate the elasticity, allows us to open the interface, and the module is chosen according to the module. So the smallest module that is around the interface. For those that you saw in the previous table, there's an increase of a deflection with depth, and we also simulated the reduced lamination of about 1 or 2 square meters with interface parameters that are very degraded, and 1 megapascal module. For this sort of category and interface, we were able to observe kinematics that were very different because the maximum deflection was obtained in the high parts of the layers. We also simulated longitudinal cracks on the entire thickness of the layer. So we had the detection basins derived, and we have 2 types of curvometers for the basin, a 0 deflection and a 3-meter tangential deformation. We see in what we present here, whether we are talking about longitudinal or that are long or short, 1 to 9 meters, a sensitivity that's about the same between absolute deflection and the simulation on a curvometer that goes of 10 to 20% compared to the non-cracked surfaces, and for the longer we have 20 to 30% of increase. For the asphalt structure and for flexible surfaces were about at the same level of sensitivity. We also then looked at the propagation of crack networks in a 3-dimensional way. This was done with what we call the frontier method. It seemed more appropriate because it looked at the various cracks which are treated as discontinuities in a geometrical sense. So I have a 3-dimensional grid of the cracks and its spread, and so this means that we can go a lot more faster and gives us a great deal of accuracy for the various cracks, so that there are less finite elements. We looked at in 3D elasticity and 3D fracture mechanics. The criterion was we used the Paris law, considering a propagation that was 3-dimensional at 3 opening, shearing, and torsion. The angle of propagation is given by the maximum tangential constraint in all of our simulations. We began to illustrate this. I'll give you one result of in Nantes with a roadway that was flexible with 60 centimeters of coverage and then granular elements, and we see the classical 18 by 30 centimeter. We position in the middle of that asphalt layer 3 fissures in different positions, cracks in different positions transversely. We're in the central area of the twinning, and this is oriented in without any pattern, and we had 20 millimeters with a spacing of 250 millimeters, and we see the propagation of the cracks which are not flat. We see them in 3D here, and otherwise you have the displacement in a maximum level at the level of the cracks. We've simulated 10 cycles of propagation, and the calculation time for 3 cracks were about at 30 minutes for computing this. Then we also looked at simulating road pavements with an open crack, which was 50 millimeters in diameter, with different cases, reinforcing whether it's possible to reinforce whether it could be filled or with a grid of the structure. The geometry is the following. When you have centered cracks between the loads and an emphatic propagation of the crack, I have here a mapping of this crack. We have reversed the Paris law, so we have a constant amount of propagation, and we deduct a number of cycles to attain this level of propagation. And for the cracks, we have a propagation of the crack which goes more quickly at the interface rather than inside the material. There's a factor of 4 between the propagation on the interface and in volume within the material. So we represented here the results of these simulations with different thicknesses of recharging, and it's important to see that it was supposed to be perfect bonding between recharging the grid and the material. So can we see an increase in the service life for propagation depending on the direction x of the creek at the interface. So to conclude, we can say that everything that's in for lamination, there's very sensitive to this in terms of position of its maximum deflection. The cracks that are vertical, whether they're longitudinal or transversal, mean that we have maximum deflections of around 1/100ths to slightly more. Can be measured by a curvometer. These maximum deflections, cracked and uncracked comparison means that this results from a delamination between layers and vertical cracks in a structure. For the structures, we get to deflections of 10 to 15 hundredths of millimeters. For the boundary elements, we did a 3D crack path, which was controlled by the maximum tangential stress, and the model shows that there's faster crack propagation at the surface than in the material itself. For the outlook, well, we would like to, for our project, we'd like to develop intersection of crack networks, which we haven't worked on at the time, and propagation directions of the cracks. And we also are looking for instrumented experiments or benchmarks because of the models that have been presented by Olivier, and this would allow us to refine the quality of the models that we've presented. Thank you for your attention.